Then, hello everyone. First of all, I would like to thank the Construct team, all the team for this event and for inviting me. It's been an honor and a pleasure to participate. I think that you are doing a great work for ROS and for the ROS community, teaching a lot of people how to start with ROS and how to do many advanced things. So my congratulations. And thank you for all the participants for attending the conference and this speech. Okay. So we can start with the speech. As we have a long title, but the purpose of this speech is to go through all the steps to have a mobile robot navigating autonomously in any environment and with a good localization based on laser, on 2D laser in this case. Okay, sorry, I forgot to present myself. Okay, yeah, I'm Román. I'm from Robotnik Automation in Spain. Robotnik is a mobile service robotics company. We do all kinds of mobile robots applications, mainly robot with wheels. And of course, we do everything based on ROS. We have been using ROS, I think, from ROSDevCon2018. I started with ROS Fuerte. So we are happy to use ROS. I've been working in Robotnik for 12 years now. Not from the beginning, but mainly we have done this kind of all kind of projects based on mobile basis. We make the hardware, the software, and this kind of things. So going back to the speech. Okay, why this speech is because I think localization and navigation is one of the main topics in ROS, and I think most of people want to know more about this topic, and there are many things to learn. Even for me, we learn every day. To do this, to follow this tutorial, you don't know an advanced knowledge of ROS. It's better if you have some ROS basics, you know about TFs, something about navigation, localization. It's going to be practical and not theory. We are not going to see theory. Okay, for this demo, we are going to use this robot, the Summit XL Steel. It's an omnidirectional platform with 4 motors and 2 lasers to cover 360 degrees. And we have another sensor, like two pan-tilt zoom cameras, an IMU, a GPS. That the GPS is not going to be necessary for this demo because it's going to be an indoors. The packages that we are going to use are these ones. You can download it from the repositories and try it in your local machine later. And now they are located. If we open the ID, okay, this environment has been new for me too, so maybe for some of you.
One question, just one question. How did you launch the simulation? Can you explain us?
Yes. To launch the simulation, you can do it in two ways. You can open a new terminal and run this command: launch submit XL sim bring up and submit XL complete. Or if you go to simulations panel, you can select the launch file that you want to run. In this case, is the submit XL complete XLS. Okay, complete. If you select and launch it, you will see this environment. Okay, with the robot and this small room. Okay, so I can wait for the people if.
Oh, it's okay. It's okay. Let's go forward. Yeah. So you all the attendants then they should try either that command or use the simulation panel and launch it. If you have some problems, ask to on the chat, so the support team will help you.
Okay. The first point of the speech is how to create a map of the environment. So first step is running the robot and the simulation. With this launch file, we are going to run the robot controllers, the sensors, the environment, and later we will run every launch file with the different packages. Okay. To launch, we can, okay, I'm going to repeat. We can select the launch file from the panel, and we have to locate the package Summit XL sim bring up. Okay, and then if you see in the screen, you have to select this file, Summit XLS complete.launch. Okay, we also need to run the RBs. In this case, is the graphical tools. So in the tool panels, you have to open graphical tools, and you will see the ROS RBs. Okay. So now we have running gazebo and RBs. We should be able to see the robot. Right now, the frame is that we are using by default is the map, the global frame. So we don't see the robot because we don't have any component publishing this transformation between the map and the base, or the map and odometry in this case. So you have to be able to see the robot model and the laser scan. You can add the sensors if you want, but for now we will just need the laser scan. Okay. I don't know if you are finding some issues. Okay. Then I forgot to mention that this launch file, it's with this launch file you can run, if you want, up to 3 robots. So it is ready to work in a multi-robot environment in case that you want it. But for today, we will use just 1 robot. So now that we have the controllers and the environment, we need to run the gmapping package. Okay. Gmapping provides a laser-based SLAM, and so we can localize the robot and create the map at the same time, and it publishes the 2D occupancy grid as a ROS in a ROS format, and we will use this data later to save the map. Okay. If you find some problems with the controllers, maybe you have to run again the launch file, because in the first times when I was preparing the tutorial, I had some problems with the controller, so run it again, the environment, it was solved. I don't know if it helps. To open RBs, you have to go to Tools, to the Tools panel, and select Graphical Tools. It will open in the same window, but you can move it to a different window or to have a better resolution or a better size. I don't know if is there anyone that doesn't have any error?
Not at the moment. So not that I am aware. No support team. Any questions related to what Román is explaining? It's okay. Everyone is following. Let's go.
Okay.
For 1 or 2 users.
Okay. So they are handling those issues. Don't worry. So you remember, everyone of the listeners, that you can ask questions to the speakers at the end of the speech. So you will have your questions, Román.
Okay.
Yeah.
And just I want to be sure that most of people is able to start everything. Okay, to run the mapping, theoretically we need 3 important points. Is that we need a 2D laser scan, a robot odometry, and the TFs being published. So as we have all of this, we are going to open a new terminal. So we can select in Tools and then select the shell, and it will open a new terminal. In this terminal, we can paste the command. So this command is going to launch the launch file for gmapping, and inside the namespace of this robot. So this is a launch for many robots, so we can select the namespace where the gmapping node will be run. So we are specifying the prefix that it's used for the frames. So once we run the gmapping, we should see this output from the laser pose, registering scans, and at the same time, if we go back to RBs and we select the fixed frame, we select Summit XLA map or the standard map, we can see that the gmapping has started to create the new map, and at the same time it is localizing the robot in the map. Okay, and once we are moving around, the map will be updated step by step. Maybe sometimes we will have to go back with the robot for if in some areas the map is not correctly done, we can go back. Okay. So there are some tips for this package is sorry for changing the windows. It is important to, if we want to create or have a good quality maps, it's important to have a good odometry estimation and to have a good laser range to be able to detect the walls always. So if we are in a really big area and the laser is not able to detect any wall or obstacle, Gmapping is not going to work because we need that information. So now we need to move around with the vehicle. To do that locally, it is easier if we use a joystick or gamepad, but to do it in RBs, we have the teleop panel. So we can add a panel and it will send the velocity commands to the vehicle. So there is a standard tool for RBs, and we have added a customized version. Is the same, but we can set the maximum linear and angular speed, and we can enable or disable the publication. Because what it does is, okay, I'm going to publish the velocity references directly to the controller. So we are moving forward. Okay. The map is being updated. Okay. So this is what RBs is seeing, and now in the simulation, this is where the robot is located in the real world. So the real world and what RBs is representing should be the same, to be sure that we are doing things well. To move remember that I don't know if by default you have the teleop panel loaded. I cannot see it, but you have to go to panels. You have it in the instructions. Go to panels, add new panel, teleop. Then you have to set the command topic for the platform, and you can start interacting with the platform. Okay. So far, how is going? Are there many issues? Because I'm reading some messages.
So yeah, the support team, any issue that is reported? Any issue?
So it's just that some users, so 3 users.
There are some users that
not getting in RVs.
Yeah.
They get it like white, the object, as if the TF7.
Okay. So yeah, they are seeing the robot in white on the RBs.
Okay. This is because you have the fixed frame is not the right one. So if Gmapping is not running, we don't have the transformation between map frame and odom frame. So we cannot see anything. When you run Gmapping, then you will have that transformation. So if you don't have Gmapping, you can change the fixed frame to Summit XLA odom. So This way, you will represent the robot related to the ODOM frame, the frame that is published in the odometry.
Perfect. Yeah, I think that answers the question. Yeah,
Okay.
great. Great, thank you. And just let me tell you to check that it's 18 minutes to finish.
Okay.
Let's go.
So we can move around to the map and create it. I have a version of the full map, so we can stop here in the mapping. Now that we have, when we have a map that we consider is good enough, we have to save it. To save it, we are going to use the package map server, the tool map saver that gets the data from the topic and creates an image and a YAML config file. So we have to run a new terminal, open a new terminal, and run the command that we have here. And it will create the map in the current folder. We can see here the files map1.pgm and map1.yaml. So with this map, so we have created the map. Now we can stop gmapping because we don't need it anymore. Gmapping is able to create a map from scratch, but is not able to load a previous map and update it with new changes. So to do that, we will use another package, AMCL, that works better for a previous created map. Okay. Apart from gmapping, there are other packages that can be used, like vector mapping, for example, or the new cartographer that already that works very well. So we go back to the terminal where we have gmapping, and we can press Ctrl+C and stop it. So now it's not running gmapping anymore, and in RBs we don't have the transformation between map and odometry. As you can see, there is no transformation with the TFs. Okay. Next point is how to use the map to localize the robot. To do that, we will use the map server to load the map that we created previously, and the AMCL to localize the robot in the map. So to run map server, we have to run this command in a terminal. It will publish in the topic the map. And then we have to run AMCL package. Okay, to work with AMCL is for other robots, what you need is a 2D laser scan, the TFs, transformations, at least from ODOM to base, and we need a map to subscribe. Okay. And so now we have the map. We are going to run AMCL. You have here the command to run it. The same. In this case, there is we are going to specify AMCL that is a holomic platform, so it can move in any direction and orientation, because it is important for the algorithm to compute the localization. Okay, AMCL is based on the Monte Carlo localization approach and uses a particle filter. So every time that we run AMCL, we have to tell the algorithm where the robot is located initially so because by default when we run AMCL, we can see the particles cloud that show where the algorithm estimates that the robot is localized. As we can see here, the localization is not the correct one because we don't have a match between what the robot is reading from the laser scan and the real map. You can see, and apart from that, you can see the particles that the dispersion is too big. So we need to reduce this dispersion to have a good estimation. So to initialize the position of the robot, we can use in RBs the tool 2D pose estimate, or you can publish it directly in a topic or even in the launch file. To initialize, we have to see in the real world where the robot is. Okay. We can see that it's close in front of the column. Okay. So now we are going to go back to RBs and more or less put the arrow in the right location. As we can see here, it's not the perfect one because we still have a mismatch between the map and what the lasers are reading. Then if we move the robot, the algorithm will find the right pose estimation after a few seconds or a few meters. So the best way to do it is to rotate the robot, for example, and to move forward, backwards. So it's enough. So now we can see that the particles, the dispersion of the particles has got reduced. So we have a good position estimation. If we compare what RBs is showing in the map and we compare it with the real world in Gazebo, we see that the localization is very good. So it's normally in the better conditions with the AMCL algorithm, we can get up to 5 centimeters of error in the best conditions. Okay, so we can move to the next point, that is how to use the map and the localization to move the robot autonomously through the map, avoiding obstacles, etc. To do that, we are going to use a move base. I guess if you have worked with ROS, you already know it. Here we have the standard diagram of move base, how it works. So basically what needs move base is the transformation that can come from AMCL in this case. We need the frames, we need the odometry, we need a map, and on the other hand, we need sensors. They can be laser scans or a point cloud from a camera or 3D sensor. And we need a base controller to publish the velocity commands. So because move base, what it receives is a goal. Okay, go to this position in the map. And the final output of move base is a velocity command. It takes in account all the environment and what the sensors are reading, and then it calculates the velocity command in real time. So we need to run move base in another terminal. So we will have 3 terminals, one for the map, another one for AMCL, and a new one for move base. Yes. Now we have running move base, and we are able to send goals to the robot. Right now we have the RBs have changed because we have subscribed to move base, some move base markers that we will see later. So to see if move base is working, we have to choose the 2D nav goal in RBs if we want to do it in a graphical way, because you already can do it through a topic or an action. So if we set a goal, the robot will move. As it is a omnidirectional vehicle, so the movement is going to use the X and Y. And so with move base, we are setting a position and orientation of the robot. You can see here the final position and the final orientation. These markers that we will see later are for the path on the cost map.
Just let you know, Román, we are 5 minutes to finish.
Okay. Yeah, we are close. We are close. Okay. When we have a move base running, some really useful displays that a move base provides are these ones. It's good to have the global cost map, global footprint, local cost map, the global plan, and the local plan. Here in RBs, in black is the global cost map. So the global planner uses that cost map to calculate the path to the final goal. For example, so this is an obstacle for the planner. And in the green line is showing the global path, and the orange one is showing the local path. The purple is the local cost map, is what the local planner is reading and it's using to compute the local plan. The local plan is used mainly to avoid obstacles in a short range. So because with the global plan, we have the ideal path to get to the goal, but the local plan allows some deviations locally based on the local obstacles that are in the environment. For example, right now we can see how the robot is moving physically. If we put an obstacle in front of the robot and we go back to ROS, we can see that locally we have detected this obstacle and we have replanned. We have changed the initial plan. For example, if we move in a straight line and we put an obstacle in front of the robot. Okay, here, wait, sorry. We can see that we have detected the obstacle and the local planner is recalculating the path. To publish the cost maps, we are using just the 2D laser, but we also can use a point cloud. For example, we can see it in this case, we have this table here, that it could be an obstacle, a real obstacle for a robot with a bigger size. But as we are just using the 2D laser that is in this plane, we just see this and we are adding just this small obstacle. The obstacle, it is inflated because in the parameters, the obstacles that you read, you can inflate them for the path planning to avoid any collisions. Depending on the environment or the accuracy of your localization, you can play with these parameters. So that's the basic points to have a robot navigating and localizing. You have more detailed explanation in the document. I'm reading this question, maybe, or we can move to the questions, or maybe I can, because the time.
Yeah, perfect. Thank you very much. Thank you very much, Román. Let's give him an applause.
Amazing project.
Yes, impressive. Impressive. Okay, so let's go then now to the questions and answers for Román. So let's see if we have any question from the support team. Any question for the speaker? Any question for the speaker? Okay, so we have here, so we have some questions here for you. Let me check. From Orlando, he says, is there a way to have the robot create the map automatically? He means without the person driving it around.
Yes. Okay, there are many ways to create the map. For example, there is I haven't tried in person, but there is a package for auto-discover the environments. So it uses an algorithm combined with, I think it's with G-mapping, I'm not sure. But in the end, what it does is to send the robot to different places on the created map or on the map that you are creating. So it's an algorithm that is looking for new areas. I don't remember the name, but
an exploring algorithm.
Yeah, if you go to the move-based tutorials, I think you will find it.
Okay, yeah, I remember one called RTT.
RTT.
Yeah.
But there are some packages working in ROS that you can try.
Okay.
For doing automatically. But
Here
in the end, normally it's better to do it manually because of sometimes you don't want to map everything, or you want to map or you want to do the mapping in a specific way to get better results.
Okay, another question from Ivanovsky. He says, Román, greetings from Valencia. What would you recommend a student about to finish in order to start working and getting into the service robotics industry? Any piece of advice for the first work?
For a first work. Okay, service robotics, I think it's a growing field right now, but there are not many. Actually, there are not many companies to work in that area, unfortunately. To start, I would recommend to learn a self-learning about ROS, because there are not so many people with good with high ROS knowledge. And companies that use ROS for service mobile applications. I think most of the new companies, or all of the new startups that use ROS, the old ones are trying to move to ROS, or are researching, because always when you move from your packages or your software to a new one, it's difficult, and for a company even more.
Okay, we have here a lot of questions that we cannot deal so many. So let me ask you just a few more. Tapas, he's asking, what is meant by localization is very good? So when you say localization is very good, so what does it mean?
That is a relative word, actually. And localization is very good is that you have a really good estimation of the robot in the real world. So you have the real world where the robot is, and you have where the robot thinks that it is. So when both of them are almost the same, is that you have a good localization. A very good localization is when you have maybe 1 centimeter of error, always, or 2 centimeters, because with that error you can go to exact positions in the map. And it's much easier to navigate to, for example, to a point where you want to pick a trolley, or you want to do the auto docking, because the robots can charge the battery by themselves. So it's easier if your localization is as good as you can just send the goal, and the robot will get to the right place. That is a good localization. I don't know if I explained it correctly.
Okay, yeah. So let's hope that Tapas has understood. So we have many other questions, but still we don't know. We don't have more time for this. The questions. It was only 10 minutes. Already used it. So that's the only thing that remains is to say thank you to Román. Thank you very much again for your excellent presentation. Thank you. This is an applause for you.
Inviting me, and I hope that it's been useful for many of you.
Extremely useful. Amazing presentation. So thank you very much, Román.